John, you can start the meeting now.
Much appreciated. Let me really quick, just for folks that are somewhat new and maybe not aware of the structure here, but there's a group of tag members. I'm just going to read through those because we've had some new additions lately, but just kind of reiterate what our the tag membership has here. So Bonnie Baxter, who's not here, but online. And then Gary is on the tag, Thomas, as well as Phil, Mark Lehman, who is maybe not online, but if not, yeah. So Ryan, I don't know if you're going to be taking over for him because I heard he was going to retire.
No, as far as I know.
Okay, well,
He decided last minute he's gonna stay on for another company. So we'll see, stays or.
all right. Well, so I guess we'll wait for whatever he decides.
I'll do with this.
All right. So Mark Lehman, who's usually out of the country, Mike Conover, then Kyle Stone is also a tag member, myself, and then the newest person switching over is Christine for Ryan. So that's our tag membership. So I just wanted to start with that, and then I'm going to go ahead and jump right in. Since I introduced you last, Christine, we'll start with the USGS update and review.
Okay. Got a lot to cover, so cut me off at any time.
John, you had wanted a kind of an overview of the partnership, right?
Exactly, absolutely.
Okay, we'll start that now. So I'll just start by also introducing Wilson Oscar. She's the new studies chief in our office, and we're really excited to have her here. So
Let me, real quick, let's go around the room just so we can introduce everybody, and we'll start with you, and yeah.
Okay. Christine Murphy, hydrologist at USGS Pacific.
Kyle Stone, Great Salt Lake Ecosystem Program.
Gary Bolofsky, University of Notre Dame.
Melissa Mossberg, USGS hydrologist.
Phil Brown, Great Salt Lake Branch Cooperative.
Mike Conover, Utah State University.
John Left.
Connor Simon, Great Salt Lake Ecosystem Program.
Serena Sewell, USGS hydrologist.
Thomas Bostons, Great Salt Lake Branch Cooperative.
Don.
Don Paul.
Jim Benson, Great Salt Lake Ecosystem Program.
Rob Baskin, Institutional Memory.
Megan Howell-Berta, Great Salt Lake Ecosystem. Carl Liddell, Westminster University.
Eric Anderson, Wildlife.
Jeff Kinlander, Davis.
Wade Wallace, Great Salt Lake Branch Farm.
I'm Westmoreland, OSI.
Yeah, Griner, interested citizen.
Marissa Lambert, Division of Forestry, Brine Citizens.
And Connor really, oh, and
I'm John Gill, Great Salt Lake Ecosystem.
yeah, and will you read off
Yeah.
who's on
So online, we've got Becca Downard, Blair Stringham, Bonnie K. Baxter, Emily Hamill, Hannah Meyer, James Harris, Jody Reimer, Lauren Head, Leanne Chambers, Linda Freitas, Mark Bell, Melissa Early, and Rob Dubuque.
All right, now you
All
can
right.
go.
Okay, so we'll start with the USGS update, it sounds like. As you all know, there's a whole host of folks in our office who make this happen, monitoring and interpretation of data. And our newest member is Melissa Mossberg, who worked with our studies and trying to get oriented to Great Salt Lake Cooperatives. So I'll be splitting this presentation with Serena, who is a hydrologist doing some interpretive work for us, and also helps with monitoring. So, so here's what we're going to cover today, and I'll try to do it quickly because it's a lot. So we'll go over an overview of our partnership with Great Salt Lake Ecosystem Program. We'll provide updates on the elevation, flow, salinity, nutrients. I'll go through some of the challenges that our lab had last year, and some lab comparisons that we're doing in an external lab to find a new way to analyze nutrients. I'll point out that our accessibility to USGS is changing, so go over that briefly so everyone knows how to access our data. And then Serena will give an overview of kind of update on the data analysis she's conducting this year. So starting with our partnership, there's two key pillars of the Great Slip program in the USGS partnership. One is water quality monitoring, and the other is more science support or interpretive work. How does the system function? So in terms of water quality monitoring, we partner with GSLEP. They collect samples every month at the 4 sites shown in the map in the south arm, those yellow diamonds. So we get monthly samples from GSLEP that are analyzed for nutrients, density, and salinity, as well as field parameters. Additionally, USGS collects samples at the inflows. So we've got Bear Bay outflow, Weaver River, Farmington Bay outflow, Godwin Drain. We also monitor the breaches, so the flow from south to north and north to south when there's flow, and on the other side when there's flow on the other side. So that is kind of our fundamental monitoring program that we engage with GSLEP. And in terms of science support, there's a long legacy of NAFs and others. Early at USGS, I'll go through some of that here. I mean, the NAFs has a long history, so does Rob Baskin. So just looking at it, cycling groups, the equation of state, this has proved invaluable for monitoring salinity in the lake, even today, certainly today. Understanding stratified flow, brine layer dynamics, internal cycle of nitrogen that was coming in. That's now being updated by Hannah McElwain, and that's currently a co-author review draft of that report. And most recently, we've been kind of putting out a lot of data releases, so water quality profiles collected at Great Salt Lake historically, as well as an update of the equation of state to make sure our salinity measurements are still robust. So these are just some examples of how our scientists supported our understanding of the system, as well as the activities that you and others conducted through the if I boil distill all that down, ways our partnership supports management of the GSLEP. Fundamentally, providing nutrient and salinity data, those are key inputs to Gary's model. I kind of have a mock-up from his paper in 2011. The nutrient data and the salinity data feed into that model. The monthly data, salinity data support management of the farm salinity and management of the firm, the causeway. And then currently we're kind of working on investigations trying to understand south arm nutrient mass that's being updated now, nutrient inflow loads, the relative magnitude of nutrient mass that is in the lake versus what's coming in. We doubled the atmospheric deposition of nutrients as well as nutrient cycling. So these types of things fundamentally providing data and then the interpretive work to better understand the system. And I just wanted to provide a little history of the funding. This is well before I came to USGS, but it looks like the agreement began in 2006, and I imagine that was with Dave Nass. And funding kind of remains, and I guess, yeah, y-axis is the amount per year. The colors indicate the amount provided by GSLEP in the purple and USGS in green. And on the second y-axis, I just wanted to highlight the, for example, lab costs we've been experiencing with these hypersaline brine samples. That's in this orange kind of dot here. So funding has, we got kind of above up in 2017, and it's remained relatively stable. And then the challenge is that we've had these huge increases in lab costs as a result of kind of restructuring of the pricing structure at the lab, and to the point where they're just charging a ton for the analysis of these hypersaline samples. So what that means is that more of our budget is being used for monitoring, for analysis, and less is available for science support. So that's kind of the reality of what we've been dealing with in the last several years. Okay, so now I'm going to shift gears, and if there's any questions, I'm happy to take time to hop in. But now I'll just shift gears to kind of updated lake conditions. So we'll start with South Arm lake surface elevation. So as of Monday, the lake elevation was at 4194.8 feet. Relative to last spring and mid-June, roughly, we were at 4194. So we're up 0.3 feet since last year's high, and we're up 2.3 feet since the low in the fall. So I'm up. If we look at the North Arm, The value, most recent value of 4191.1 feet. Last year, the high in March, really it didn't come up much, was 4189.8 feet. So we're up 1.3 feet since the high last year, and we're up 2.3 feet since the fall. So the North Arm is coming up well. If we consider surface water inflows, we'll start with Corinne, Corinne. This plot many of you are familiar with, but we're looking at cumulative stream flow and nice big feet on the y-axis. We start at the beginning of our water meter, which is on October 1st, and then it flows just added day after day after day. The blue line represents the record max. The orange line is record min, and then this kind of green hashed area is the 25th and 75th percentiles. The gray line is median. So for this site, we are sitting right around the median value for this gauge, this record. Looks pretty good. For Weber, we've been kind of hovering around 75th percentile. In fact, near the median, and now we're coming back up again for the Weber. So that's also positive news. And then at Farmington Bay, we're hovering right around max value for Farmington Bay. And for Gauguin, we're above 75th percentile. Lots of water comes down in Jordan. We're seeing that in our cycles. I also just was curious about what the discharge is looking like. So the mean daily discharge on the y-axis started in October 2022. You can see the big peak last year for our 4 inflow sites. We're starting to see flows sort of gradually come up for Bearberry and Corinne, certainly for Gauguin draining and also for Weaver. Farmington kind of did this little mini peak and has now come back down a little bit, but yeah, we're starting to see runoff ramp up. Okay, these are just a record of our measurements at Bearberry Bay outflow. So if you recall, we don't have a gauge there. It's a 500-foot wide cross section, really difficult to gauge. But we have been making measurements there. There was one, I think Angie made one in March, but it wasn't able to get it in the database, and that was around 2,500 CFS. And this one at late February, it's about 5,800 CFS. So quite a bit of water is coming in at the outflow too. And I will say we were able to acquire additional funding to monitor this more. And so during runoff, we're going to be going every 2 weeks instead of every month or so. So we're hoping to get more measurements of flow at this site. And we're also, there's a number of different funding streams that are helping us try to develop a gauge there. So there's a surface velocity radar instrument there that is measuring surface velocities. We're working with Utah State to try to figure out how we might build a model to try and get continuous discharge there. It's a very challenging site, but we're trying to instrument it in various ways to tackle it, because we know it's really important in flow. If we compare, this is a plot just showing discharge at Corinne. So that's where we have a gauge, a continuous gauge that's above the refuge. And then comparing that to our discrete measurements at the causeway. And you can see kind of in these more recent measurements, they're deviating from the Corinne gauge more and more. And in fact, through saline lakes we recently did, we've been doing these, we call them lower Bear synoptics, where we just take discharge measurements from a whole bunch of different locations through the lower Bear. And we're actually finding a lot of flow is coming in kind of the Bothwell pocket and downstream of the refuge. And so that it makes sense that we're seeing a disconnect here between what's measured at Corinne and what's coming in at the outflow. There's just these ungauged flows that seem to be contributing quite a bit of flow to the outflow right now. All right, we've reached flow monitoring. You are all aware that yeah.
So last year you didn't have that contractor anymore.
Yeah.
So what would that be?
I'm wondering if there's just, it's like, you know, could be, I guess is that soils are more saturated. It's just more efficiently running off that area, the Bothwell pocket. I'm not quite sure. Yeah.
Okay. So earlier this year, there was some infrastructure repair being done in the Weaver River Basin. And so they were short circuiting or I guess redirecting flow through Lord Bay Reservoir.
Okay.
And then releasing that out the north side of Lord Bay, but then closing the spur and out.
I see.
So that could account for some of that as well as some of your
That's really
early
good.
on in the river. So
Okay. And that's like what time period?
I have to look. Ray Shanson works here. So that's
great. Okay. Cool. That's good to know. Okay. we breach, we monitor this, we conduct monthly discharge measurements of the breach. So again, this is on the railroad causeway where we historically have had a couple of stops north and south. We conduct monthly discharge measurements. We also have a number of different monitors out here. So continuous lake surface elevation on both sides of the causeway, we've got weather sensors, and then uplifter ADCT or ADBM that's monitoring velocities. And we collect this data and work very closely with Utah State because we're modeling the flows here. And what's really great is that now, as of they modified the berm, the most recent update or raising of the berm was February 2023. It eroded out last. I guess he's able to go back. I think it eroded. Jeff can remember. I think it eroded out in June of last year and created that match. And that created conditions that actually allowed us to develop a rating curve. So there's now a fairly predictable relationship between lake stage and flow. And so Andy Carlson has been able to develop a continuous record of discharge from south to north because there isn't enough north to south flow right now. And that's available online if who wants to see it. So I only pulled the last week or so, but we're looking around 15 to 1,500 CFS are flowing from south to north at the moment. And you can Google it, but here's the website to access this data. And we're also, in addition, as part of that, collecting monthly discharge measurements. So Andy's continuing to develop this rating curve and evaluate it. But it's really exciting that we have that now because this has been we've been trying to do for a long time. And it's just fortuitous that the V-notch weir, unintended V-notch weir is allowing us to do that. Okay, switching gears to salinity. These are salinity values from our 4 GSLEP sites on the south arm from about October 2022 to present, and our most recent measurement is from February 12th. We just got samples today, so we're excited about that. Salinities on grams per liter on y-axis. So as of February 12th, we were looking at 100 to 128 grams per liter. We're about 16 grams per liter, 15 to 20 grams per liter fresher than fall's values when it kind of peaked, and certainly much lower than our October 2022 values when we were much higher. We are starting to see a freshening at the surface. So we compare half meter, 3 meter samples, we're seeing like a 3 to 8 gram per liter difference. And at depth, if I recall, it's what they're about 136 to 138 grams per liter at these sites. So we are kind of seeing a vertical gradient being established, but by and large, these are really good. They're within this optimal range that has been. And we also have recent measurements that can reach 114 grams per liter as of March 6th. And as of March 25th, so we collected a sample of that 115 grams per liter at Salter. That's what we got for salinity. All right, so now we'll switch gears into nutrients. I shared this plot at the last tag in December, and I said we don't have any nutrient data past February 7th, 2023. So these are our hypersized saline lake samples, all of our analytes for nutrients. This is still the case. We still do not have data. And so while we have still been collecting samples, lake samples have been collected from October. We've got October, November, December, now February and April. So we're getting samples in both for inflows and at the lake, collecting them. Our lab is not analyzing them. And so that's what I'm going to go through now is our lab challenges we've been experiencing. I think Brian wants to start off by saying the water missionary at USGS has been going through a lot of transitions, a lot of reorganization in the last few years, and that has impacted the lab and their organization, how they're pricing things, and actually is affecting their ability to get analysis done. And so the reality is that this year we've had a number of personnel issues and a number of equipment failures that led to them not analyzing samples that we've been sending them for months and months and not actually telling us. And so I'll just go through this. Here's the list of analytes that we submit with the samples that are collected in the south arm and the samples that are collected from freshwater inflows. We've got total nitrogen, dissolved fraction, ammonia, nitrate, nitrite, and nitrite, and then our phosphorus, phosphate. So the good news is that we have inorganic nutrients results for everything. Last summer, they did have a hard time meeting the time, so that will be something that we just scrutinize as we QAQC the data. The unfortunate part is that for total nitrogen and total dissolved nitrogen, the lab stopped analyzing our brine samples as of April 2020. And they just never notified us. And how this is a little bit confusing is because the lab operates, they'll hold data for quite a long time until they QAQC it and they fix all the things and then they release it. So it had been, it's been a while and it's like, okay, it's been long enough, they should be releasing this. And they pinged and 2 months later, they got back to us and said, just not been yet. And so that's very unfortunate because the holding time on these samples is 30 days. For freshwater, they had been analyzing them for a longer period of time, but they also stopped analyzing these in August 2022. So as a result of personnel issues, as a result of equipment failures, they lost their autoclaves, a lot of things happening. On phosphorus, it's also a little bit better. They stopped analyzing these total phosphorus and total dissolved phosphorus analytes in October 2022. And so Hannah, when we met, we started meeting with the lab pretty regularly to figure out, well, what data did we have, what data did we not have, how did we move forward? And she was really instrumental in all that process. And what we decided is that for the South Farm data, again, we stopped analyzing total nitrogen and total dissolved nitrogen in people. We decided we were going to kind of forfeit the samples from April to September. And then we're going to have them analyze samples that have been collected from October on. And the logic there is that we want some data. These totals may be a little more, we may be able to analyze them, you know, an exceedance of their holding time, so they're a little more stable, a little less labile. But we didn't want to pay for all the samples from 6 to 8 months or a year ago because they're very, very expensive. So we tried to find this balance between getting some analyses and forfeiting ones that we just didn't think the data quality would be very good. So that's what we decided to do, is we're going to analyze total nitrogen, dissolved nitrogen, phosphorus, total phosphorus from October to December. Again, holding times have been exceeded because they're still working through a backlog of thousands of samples. And luckily, the lab is evaluating the effect of full-time exceedances on nutrient analysis. So we'll have more clarity moving forward on the effect of the full-time exceedances. But what that means for GSLEP, bottom line, is that we're losing monthly total dissolved nitrogen and nitrogen for April to September, and that 48 samples are going to be corrected. For the new breach, these are also hypersaline, so they were affected as well. So samples collected from April through July will also be affected and not have total nitrogen or total dissolved nitrogen data. So that affects 6 samples. And then for the inflow sites, we are going to lose the August 2020, and that affects 8 of our samples. So we just wanted to be transparent about this, that this has happened and that there will be a kind of a gap in the data, especially for people who use it. How are science and monitoring going to be affected? Okay, in terms of science, we're going to have an 8-month gap in South Farm total nitrogen and total dissolved nitrogen. That will affect various modeling and analysis that he's doing. The nutrient results from October through January may be adversely affected. We're going to see what the lab says and the results of their study. And it does affect our ability to quantify South Farm nitrogen mass in 2023. And we were really curious to see what that was, especially following our modifications that to the February. So, and there could also be impacts to the quantification of nutrients coming in, although those will be much less significant than the South Farm and analysis. And in terms of monitoring, this is really motivated us to find a new lab. We already started doing that about a year ago. And we've slightly modified the sample collection and we've communicated that to So moving forward, here's what we're going to do and what we've started doing already. It's basically as soon as Hannah and I learned of this, we learned the magnitude of it, we've pivoted for February. So the samples that were collected in February, we've stopped sending the total fraction to our lab, knowing that they were way behind and that they were likely not going to analyze those in time. And we pivoted to Chesapeake Biological Labs, which I'll talk a little bit more about. And so now we're sending split samples. We're sending a subset to our USGS lab for the inorganic nutrient analyses, so ammonia and trait nitrite and orthophosphate, because they're actually analyzing those on time, and they seem to be doing a good job with those analytes. But we are sending a second split to Chesapeake Biological Labs for the whole suite of analyses, so that we can get data coming in at that lab and actually get results for stable for nitrogen and phosphorus and stuff. So that's kind of where we are with that. And any questions before I go on? Okay. All right, so now Hannah came up with a really great set of slides here, and I will do my best to get to the sheet we made today. But these basically go through the new lab that we found and that we're working with, to give you a sense of the steps forward. And she's kind of outlined here. We actually started working with this lab as of last year because of the cost. We knew we had to pivot and try to find a more affordable source of nutrient analyses. And so we started that about a year ago. So luckily we collected samples in June and October, and we have some comparison data from June that we can start looking at. And we're going to continue to build those data sets to evaluate how this lab is doing. These samples are very difficult to analyze. They're super salty, and a little flow equipment doesn't like that. They're loaded with all kinds of trace elements that might have interferences with reagents to add. So it is a challenge, but we're starting to build that and make sure we evaluate this lab for last week. So Chesapeake Biological Lab, they're a subsidiary of University of New York Center for Environmental Sciences. They provide analytical support to a number of different institutes. And they've been doing this for a long time, as I understand. So they're a full service lab. We're working with the Nutrient Analytical Services Laboratory, and we've had a number of calls with their lab chemists to try and go through some of the unique characteristics of brine brine. So yeah, okay. Hannah is very thoroughly in comparing methods. So from Chesapeake Biological Labs to our lab, National Water Quality Lab. And these plots I'll show you for each analyte. So we've got our lab's data. This is concentration, in this case ammonia, on the y-axis, and then the Chesapeake Biological Lab on the x-axis. And so ideally, on a plot, if these labs are saying the same thing, they will land on this one line. And so we're a bit worried about is systematic biases in these results and shifting to another lab where we're going to see a step change in the data. So this is a concern. So in the case of ammonia, Chesapeake Biological Lab is basically under-reporting ammonia relative to USGS. And again, our lab had struggles with holding time violations last summer. So there's questions on both sides. So we'll just put this data, but this is the best we have. Nitrite, these are tricky because they're often below the detection. And I honestly don't think we'll ever get good comparisons for things like nitrite and trait because the concentrations are so low, uncertainties are really high near the detection. Nitrate, similar thing. We're seeing the kind of king out of the detection limit here, but by and large, USGS labs are, well, I guess below this. So. Or the phosphate looks a bit better. That's encouraging. It does seem to be systematically pretty high. But this is just to kind of illustrate that we're tracking these data. We're doing our best to find a replacement lab. And unfortunately, our lab at the moment is not a good option for the total fraction. Okay. All right. And then the last thing I'll go through is that accessing USGS data has changed a bit. So for those, yeah.
Just a question about the labs. Do you compare the protocols? Are any consistent?
They are, so yeah, that's kind of what Hannah had done for these. So kind of a summary of the methods, they are different. Like they might use different reagents. They might use, I mean, they're essentially the same. They do a digest, they add a reagent, they look at a colorimetric response. But the reagents might be slightly different. a USGS was matrix matching, so for like standards and calibration curves, they were actually making a hypersaline solution and adding nutrients to it. So yes, there are differences, which
Is there a reason for each one better than the other?
well, I think we had kind of considered USGS to be the best because it had been so scrutinized for many years by various lab chemists, and they had thought about these things, they had thought about working with the brine. And so it is a bit tough to go to a new lab where they're like, oh, we'll just delete it and it'll be fine. And we go to the ocean water. Well, there's a whole bunch of stuff in this brine that might react with your reagents. And so, and they're open to that. They're open to helping us do comparisons and things, but it's not straightforward. So we've always considered USGS to be the best. And I think in a round robin or something, they determined that the USGS lab was kind of, was a good option to go with. It's just that we're being priced out. And we have been fighting with the higher ups to say, you're pricing us out of our monitoring program. And we have not gotten much understood from that. But yeah, it's just the reality of where we're at.
This has to be occurring nationally though, with programs of water monitoring, and the cost is going up.
Well, they went up especially for the brines because they said we're gonna charge you exactly what this costs, and because it costs so much more to do matrix matching and it costs so much more to do these various things for the brines, they started before it had kind of been subsidized. There were national programs that had been subsidizing these analyses a little bit. They restructured their pricing and said we're going to charge exactly what everything costs, and they went through a cost analysis of everything, and that's kind of the result, is that these are really hard to analyze. We're going to charge a lot. Yes, but we have seen increases in our freshwater nutrient analysis. Not the same magnitude.
When you said the two labs don't agree on the total nitrogen, is it a consistent underestimation or overestimation, or is it a poor regression fit as well? What kind of mismatch is it for the total?
We don't actually have totals yet.
Oh,
Because and these data are from June, and our lab didn't provide data. So while we had this external lab, and now the whole idea is to do comparisons of everything, we didn't realize our lab wasn't on. We don't have that yet. But as soon as the lab gets back on there, we're in contact with the chemist. So, okay, what's your backlog? Like, as soon as they're back and caught up, we're going to start sending them total nitrogen samples again, so we can build these comparisons with the external lab.
I just want to go back to something Kyle said on the lows for barrier pay. So he hit on that there was some water being released out of the river bay at a certain time. There was also some water released in additional water released in, I believe it was September.
Okay.
Out of the river bay. There's also a bunch of water being released out of the river bay right now. That you're not. There's no measurement. That, I mean, there is, but there isn't of what's coming out of the bay.
Okay.
So that, just so you know what's going on.
But I asked who managed that? Like if we wanted to learn about those flows, where did we?
So we were based,
Okay.
because they managed, Willow Bay. So we were based on our concerns.
Thank you.
I've got the data on what they're releasing if you're interested, so.
Okay. Great.
Yeah.
Last thing I have before Selena is going through how data accessibility is changed. So how many of you use shift data or try to access this shift data? Okay, cool. Okay, great. I just wasn't sure. So you might be familiar with Endless. That's how we have been accessed. That's being modernized, which means it's going away. And pretty soon, there actually will be no more data being uploaded to this starting in March. So I want to highlight that there will be going to be a public webinar for folks that we're going to it's scheduled for April 11th. And when we get the link to this webinar, please let us know, we'll forward it to everybody who's interested in learning. It's basically going to walk public through how to access USGS data with this new system. And Hannah wanted me to point everybody to this blog. This is the Water Data for the Nation, WDFN. Has a bunch of information on how to access our discrete data in this new system, and folks want to take a look at that. And I'm happy to provide these links later if anyone's interested. But super heads up, how we access water quality data is changing. Not flow, that's going to stay the same, but the water quality is changing. And the whole idea behind this modernization is to, make it more functional, provide more services. There's tables, there's maps, there's ways to download the data. So hopefully in the long run, this will be better. It'll be a better system for everybody to work with, but it will be a transition as we all learn how to a new way. There's going to be two ways to access it. This new water data for the nation. That's a USGS kind of portal. And I did it this morning. It's not too bad. To type in the site and get some nutrient or leaky data. Sits out of CSV. The other way is this water quality portal. And this is actually kind of a hub for state data, county, all kinds of different entities store their data on water quality portal. So you can also access USGS data there. There'll be a couple of different ways. And then Hannah just wanted to say there's many ways you'll be able to search for the data. So with a site list or with a boundary box, region, hydrologic units, that's kind of like a mini watershed. She also wanted me to really highlight that there's now these observed properties. So for those of you who are familiar with USGS key codes, parameter codes, those are going away. And they're going to be replaced with these observed properties, which are supposed to be more intuitive. So maybe you'll search for something like salinity instead of key code 70905. So hopefully it'll make things a little bit more. But yeah, with that, I think that's all that I had. And turn it over to Serena and her updates. Once you have any questions.
Hi, again, my name is Serena Sidol, so happy to be presenting to you guys again. Okay, so let me just. Okay, so last time we were talking about the GSLEP agreement goals, and we are using again just to remind ourselves of data since 2010. And then we wanted to look at this data to review monthly nutrient concentrations via 3 main analyses. We wanted to assess seasonal variability in the South Arms Red filtration to evaluate the likelihood the Great Salt Lake is or could be a phosphorus limited system. So, and again, this is just to look at, because of rising costs in lab, to see if there's any way that we could trim down our sampling to see if we can save costs that way, or if we really need to keep all of the sampling that we're doing, just because taking away the value of the science that we're getting, that information. So that's a quick reminder of what these slides are about. All right, so key points and takeaways, these are mainly for the Redfield ratios. The first one is that the Great Salt Lake is mostly an N-limited system. Deeper samples do show more P limitation. Samples that are deep and closest to the breach, especially 2565, show a higher tendency towards P limitation than other locations. Water availability may contribute to nutrient trends that we're seeing. And then also nutrient availability may also be influencing processes going on at the breach. So let's dig into that a little bit. So this is looking at all of the samples. And again, we get these samples from the GSLEP collection. So those 4 sites that Christine went over. When looking at all of those samples together, we see that 76.2 of those samples are N-limited and about 23.7 of those samples are P-limited. And again, we were looking at meat and organic samples, if you remember. And if you look at here, these are the shallow samples here in this more salmon color. Deep samples are the green color, and we have transitional samples in this blue color right here. So mainly we're going to be focusing on the shallow and the deep samples and contrasting So here, we have the shallow samples in the salmon color still. We have the deep samples in this green color here. This black line right here is that 16 ratio. So that red filled ratio. We're going to go with that ratio. We'll talk a little bit about different ratios a little bit later depending on phytoplankton, but we want to mainly focus on that 16:1 ratio for that red fill ratio here. So if we look at just the shallow to deep, we see here that in the shallow samples, it's 20% P limited and 80% N limited. So there's a lot more here that are limited in the shallow samples. If we look at the deep samples, that changes. We have 37% that are P limited, and we have 62% that is N limited. So there's a little bit more P limitation going on in those deep samples. Okay, we're just looking at shallow samples now. So the pattern may look familiar, but we're highlighting also the station here. Ignore this, it copied over here. So just remember here, 20 and 80, not 20 and 20. So excuse me for that, but there's not really any particular pattern that sticks out in the shallow samples where there's definitely one station or another station that has more or less P or S limitation. So we don't see any strong pattern in the location for those shallow samples. If we look at the deep samples, the station name again, we're looking at the sites of 2565 and 3510, and the P limitation and the N limitation is listed again. We do see slightly that 2565 does exhibit more samples that have that P limitation, and that will be highlighted again in just a minute here. So these are the locations of the sites. What I did here so that you could see all of the samples was take the point and expand everything out. So it's not like these are different locations. It's just one point that I've blown up kind of to say. So keep that in mind. These are all the samples together, and the light pink color is everything that is N limited, and then the black is everything that is P limited. And you can see, looking at all of the samples, that it's kind of hard to pick out any kind of patterns spatially of what is going on. Some of you with that might be looking at 2565 going, there. So again, if we look at just the shallow samples, low cal doesn't really stick strongly out in any of these samples. There's a lot of unlimited samples. Everything's looking good. And then if we look at the deep samples, we can visually tell that again, 2565 does have more samples that exhibit that P limitation. And looking down here at 3510, we see that there's P limitation occurring, but definitely very visibly noticeable here at 2565 that there is more limitation going on. So. Okay, so let's look at these shallow samples again. Again, if we are looking at this graph, we have red fill ratio over here on the y-axis and data here on the x-axis. This black line represents that ratio of 16:1, looking at the red fill ratio. This is the colors associated with the season, and then the shape is associated with the station. So looking at this, we can see some patterns coming up over the year 2020 kind of beyond. There's some grouping down here. And we can kind of look at, we do know that from 2020 to 2023 was a period of water deprivation or lower lake levels. And that we can kind of look up here and we can speculate, we haven't done into anything yet, but we can speculate that that may be affecting the nutrient availability and therefore the red fill ratio here. And again, in this picture, the lake stage at Great Salt Lake, Salt Cove Harbor, and then those changes that are shown here. So there is lower lake levels going from 2020 to 2020. So again,
That's something to look at.
we haven't looked into that yet though. Looking at the deep samples, the same kind of a thing. We have red field ratios over here on the y-axis, and then we have date over here on the x-axis. We have the black lines representing that red field ratio 16:1. The color is the season, and then the station name is the shape. So we see this kind of like rainbow up here. And again, 2016, we see kind of this lower grouping here, and then that starts to rise and dip down again. And something that we could look to that might be a third spot is processes happening at the breach. We do know that prior to 2016, when the breach was reopened, so right here, the deep brine layer had completely disappeared. And then the deep brine layer reformed as early as July 2017 here. So the breach processes could be affecting what we're seeing here when we're looking at red field ratios. Yes.
It looks like, since the deep brine layer has mostly disappeared now, it looks like that trend is coming back slowly forward 2017.
Yeah.
I mean, it's not confirmed, kind of a trend.
Yeah, and that might just be because it's a more stable environment now than it previously was, that we have that shift occurring here, and that's what we saw. But we haven't been able to dig deep into that yet.
Well, supporting that, there's a site pattern there from 2022. You notice the ones that are strongly unlimited down deep. It's 3510. That's the first site that the brine layer disappeared from on this last cycle. So if that might be part of it, yeah.
Yeah, for sure. It's a good spot on that too.
So is there a process or a hypothesis as to why that would be when there is a deep brine layer to get, more of that phosphorus irrigation and these are the red field irrigations versus when the brine layer is not there? A hypothesis and why that might be.
Go ahead, you have any thoughts on that?
I mean, just that the nitrogen site is cycling differently in the deep brine layer, and there are conditions down there that are off-gassing or, patient just losing nitrogen. I don't know, that's one guess, one hypothesis.
Yeah, we haven't dug deep into those questions yet, but they're cool questions to ask for sure.
Mhm.
All right, we also were able to look at phytoplankton and different species of phytoplankton and saw how that affected what ratios we were seeing and what percentages were either E limited or N limited. So if we look at Denaliella, it has a range of 10, about 10, we use 10 in this to look at red field ratios and how that would be affected if we use a red field ratio of 10 instead of 16. And then
Now you did it.
now I can did it.
You're really. Technology.
Yeah.
Okay. And it did affect it. So if we look at the shallow samples here, there's definitely more P limitation that's going on. So 55% is P limited and 45% is N limited. If we look at the deep samples, it was very much affected. So we have this 90% P limitation as compared to 10% N limitation. So very different than looking at a ratio of 16:1 for these. And there was effect for, I'm going to pronounce these incorrectly, so I apologize. These not affected. I should know them, but, no, okay. We'll leave that to you. But these, we put at 15, so instead of 16, we had it at 15. And we did see some effect of that too. Not as much as 10, but we did see so much. So 25 P limited in the shallow samples, 75% M limitation in the shallow samples. And then 46% P limitation in deep samples and 53% N limitation in those deep samples. So a little bit different, but definitely if we're looking at vanilla at that 10 ratio, it does change it quite a bit. We're moving on to the next part of the agreement. So looking at sensitivity analysis of inflow nutrient sampling to evaluate the effect of decreasing in frequency. So getting more into at what number of sampling can we decrease to that would not affect the science or that would affect the science. So we're working with running this Coleman function, and this function uses an autoregressive model to produce more accurate estimates of concentration and flux. So we're seeing how that changes depending upon the number of samples that we take each year. So normally we take 9 samples, and then we want to see what it looks like when we reduce it down to 6 samples and then also reduce it down to 4 samples. And that's an ongoing thing that we're doing right now. This is previous work that has been done by Christine, some code that she put together. This is an update to that code that I'm currently trying to run. There is a little bit of a hiccup just because, as Christine mentioned earlier, we're transferring over from like an endless system over to query-based sampling, and pulling that data takes some different coding, and so that's really fun to update code. Anyway, so this is what we previously looked at. Again, we're going to update this. I don't imagine it will be drastically different, but it will be updated. And we can see here, this is the percent error in total phosphorus, percent error in total nitrogen. These are for Farmington Bay and Weaver, and this is for Goggin for Bear River. This black line right here is normal sampling, so that 9 samples per year. The yellow is if we brought it down to 4 samples per year, and the blue is if we brought it down to 6 samples per year. Then these are in that 10% error thing. So we want it to stay within 10%. And you can see that, so if we look at, for instance, Farmington Bay, that we deviate out of that 10% if we go down to 4 samples per year, but we can stay pretty comfortably close if we stick to 6 samples per year, for instance. So, and that changes per site and for the nutrient that we're looking at too. So for instance, if we have Weaver River, we have these patterns that we see. For the most part, 6 years tends to stay, but it does deviate sometimes after that. And that's what we want to stay away from, just because we want accurate and good science. So again, we're working on updating this. I was hoping to have that updated, but the code, you know, so but it is interesting. We're excited to be looking at this. Yeah, any kinds of questions on direct field ratios or anything else? Almost a question, and not quite. Okay. Well, thank you for your attention, and that's what we have. This is contact information here. Don't contact me. But please have that. Okay. No, thank you.
Anybody got any questions for the USGS crew? Yeah.
Then Christine, did you think of looking at other ratios, but the red field ratio?
Just the ones that.
Only the ones that algae,
Yeah.
We are where the
Nothing with total nitrogen versus dissolved.
We kind of early on had considered doing whole, total but from what we could tell, Gary had used inorganic nutrients and others had used inorganic. So, the the way we're thinking about it is what's most viable to the phytoplankton. But, yeah, that would be another way. You think that would be useful?
I mean, there are some publications I think that mention that different ratios that can be more useful. With the sort of recycling that's going on. And we're still recycling.
There's some recent papers too that have questioned the 16
Yeah.
on Redfield ratios, whether that's really phosphorus versus nitrogen.
Yeah.
I know, and like systems can be tricky with Redfield ratios too. And what are correct.
Right.
There's a few papers that promote using DIN versus total phosphorus depending on the system too. So it can get complicated depending on what you're looking at. And you'd almost need paired detailed laboratory studies for the community in question to see algal response based on the constituents you're measuring. So it can get hard.
Yeah, in the 2011 paper, when we did the inorganic ratio, I did try to use totals dissolved, and it gave some really weird ratios.
Yeah. Okay.
Well, part of the takeaway that I get from that is, we keep shrinking our budget to try to keep up with, maybe one of the more important things, which is trying to understand nutrients on the lake. And, it's like golfing with a blade of grass. We keep whipping at it, but we're barely moving the ball. So,
One other issue, the nitrogen phosphorus ratios you got that I sent you for the phytoplankton. We don't have any idea how variable those are in terms, well, we have variability of the samples that we analyze, but we don't know how variable they are in changing that ratio under different conditions.
Okay. Thank you. That's it.
Just a word of caution.
Yeah.
I treat them as constants too, so.
No, it's hard.
all right, so going from not so good news to a little better news, maybe with brine shrimp demographics, we were able to get some samples and analyze them. So I'll let Connor and Kyle tag team this one.
Oh, is that that's a tag team then?
Yeah.
Okay, so moving forward. So I've met some of you I have yet to meet. So my name is Connor Simon. I'm a new biologist here with GSLEP. I started in December, kind of taking over for Ashley. Big shoes to fill, but we're working on it, and I'm just happy to be here. But yeah, so Kyle and I, like Love said, we're going to tag team this puppy here today. I'm going to handle the first bit where we just kind of go over how the brine shrimp have been behaving, how the population's been faring over the past couple of months. And Kyle's going to take over with the predictive model. Okay, so these figures should look familiar if you did the tag before. For those who haven't been to tag, I'm going to go over the legend. So for the dotted lines that go stepwise, those are maximum and minimum values based on data since 1999. The shaded gray areas are the 25th and 75th percentiles, also since 1999. The solid black line is the average from 1999 for whatever parameter we're looking at. The dotted black line is the 5-year average. So for this current data, we're looking at 2019, 20, 21, 22, and 23. And then for the average of 1999 and the 5-year average, so that average for plotting purposes is put at the 15th of the month. So the actual position of that average within the month isn't really what you should focus on. It's more the actual amplitude of that line. The gold or yellow line, and that is the previous year, and then the red line is the current year. So for previous year and current year, that's raw data. Those are not averages. Okay, so for all of the figures that I'm going to be discussing, the x-axis is going to be the month, and the y-axis will change based on whatever parameters we're looking at. This table shows the average for the first 3 months, which is all that we're going to be reporting about today. So this first figure here is looking at temperature, y-axis, degrees temperature, degrees Celsius for temperature, and this is water temperature. So going into January, we were right around average of historical trends. We dropped down below that 4-year cutoff, triggering some adult death. But what really gets interesting is going into February and March, we were well above average. We actually set some new maximums near the end of February for water temp. But this has implications for hatching, which also for salinity. We're going to get into that later. But so for temperature, the big takeaway is that we are above average water temp moving into the year. Now we're looking at salinity here on the y-axis, salinity in percent. So you're all aware this is salinity measured at the surface of the lake using a refractometer. So in January, we were at about 12.6%. That dropped into February and March. So in January, we were right around average. And then this dropped significantly moving into February and March, setting 2 new minimums for the lake in both of those functions respectively. So again, this combined with temperature is going to promote alveoli hatching. We'll get to that in a little bit. But this is probably due to precipitation that's happening during these months. You've got warmer temperatures, the runoff from the mountains entering the lake, and then also the reservoirs were all full from last year. So all these managers are trying to dump water into the lake, trying to get ready for the next runoff from the snows. Here we're looking at chlorophyll abundance. So on the y-axis, chlorophyll concentration measured in micrograms per liter. Now this is kind of interesting. So moving into January, we actually saw a decrease. Now this is because during January, we still had some adult shrimp left in the lake. So they were grazing down, continuously grazing that algae, decreasing that chlorophyll. And as that temperature below 4 degrees persisted, adults continued to die off. And then that combined with increasing temperatures, decreasing salinity, and all that runoff, bringing nutrients into the system. You got that big spike that happened in February into March. Well, right before March. So chlorophyll abundance increased, and then this increasing temperature, decreasing salinity, that caused alveoli hatching. So alveoli started to hatch, and then that peak dropped rapidly. So you have alveoli grazing down the chlorophyll, decreasing chlorophyll abundance. Persist density, now we are lower on the edge of historic levels. In January, we had a little bit of a spike and then a decrease.
Thomas, did you have a question?
Yeah, go for it.
Would you mind going back to?
Yeah.
How many years of salinity data is that?
That's 690.
Oh, 99?
Yeah.
99, that's salinity South Arm was around 7 ppb. Even below that. So all of that lowest salinity.
But there's not a direct connection between PQC and. Yeah, so that's saying they don't get a right top of the data.
Yeah, they had.
So this, what, roughly 9 for PQC. It could be a couple, but we had that 80, 85 grams per liter.
And I'll go back and look at our data, so it went down to around 7%.
Okay, let's, no, fair enough. We can take that. Okay. So the persist density, we were talking about this little peak that we got here. Now our January ones were interesting. We ended up getting a 32, a 78, and then 2 9s in a row persist per liter, which is what we're presented on this y-axis. So that's generating this peak decline, and then it's been relatively stable. Now, as we're moving into February and March, this is going to start declining as cysts are hatching, alveoli are emerging. So now this is the figure I've been referencing. So here's alveoli. So for density of alveoli on the y-axis and number per liter, moving into January, there were still some left in the lake. Now this likely wasn't hatching of cysts. This was likely the first birth. Some alveoli emerging from females that were left over from the previous year. And then in February, we have a little bit of overlap here, but alveoli began hatching. So we have those elevated temperatures, decreased salinity, we have food. So hatching started in February, and then it really ramped up in March, which is this very steep increase that you can see happening in mid-March, setting a new maximum for alveoli density in the lake for this time period. Now, what's interesting is that relative to historic trends, this is early. This is very early.
And we were really worried about a second winter coming around and wiping out the Alveoli population, but as you guys can see, it's looking pretty nice. Yesterday on the lake was gorgeous. So it's looking good with regards to that. But so we are definitely continuing with the hatch. The population is increasing. So for juveniles and adults, all the different females, males, all that, it's a similar story. So I'm going to kind of blaze through these, but in January, there were some juveniles. So this specific figure is showing juveniles in number per liter. In January, there were some that persisted from the previous year. In February, we have die-off, and in March, we also have some juveniles present in the lake. Now it reads 0.00, that's just for significant figures in the table. It was actually a small number of individuals in the lake. Now this is likely those nauplii that are starting to age, go through their life stages in the month of March. So they're going to pick up some juveniles in the lake. For males, similar story. In January, there were some males left. February, it died off. And then in March, we actually started observing some adult males in the lake. So these are these nauplii advancing through their life stages, just barely identifiable as adult males. Females, same story. January, there were still some left. February, we started to see die off, and then nauplii were advancing through their life stages as of March. Now for females with eggs, which is represented on this in this figure, in January, there were still some females with eggs. As of February and March, they've all died off. Likewise, females with cysts. January, there were still some females with cysts present in the system. February and March, they died off. Now, all of those females that we've been seeing are not quite reproductively active yet. They're just barely identifiable as an adult female. Now, this figure shows pretty much that whole story with adults. So this is showing total adult density. So that's males, females, females with eggs, and females with cysts on that y-axis. Again, we're still in that number per liter. In January, we still had some individuals left over in the lake. That's causing that chlorophyll to decrease. Moving into February, all those individuals pretty much died. That let the chlorophyll abundance increase. And then moving into March, we're now finally starting to see some of those nauplii aging, advancing through their life stages, and becoming reproductive device. Okay. And then I'm going to pass it over to Kyle. So that's it for the population, what's been happening in terms of brine shrimp for the past couple of months. Kyle's going to handle the predictive model. Any questions on?
Yeah.
All right, harvest prediction. So we're going to go back to bring a 2023 forecast and see how we wrapped up in 2023. So if you guys all remember last year, coming into 2023, we were really kind of lower on this density independent side of the curve, the red circle that you can see here, between 19 and 20 cysts per liter. And the concern was, did we leave enough cysts in the lake to hatch? That was one of the things we were worried about. The original thing, we would have expected somewhere between right around 130 cysts per liter in the fall. Which really wasn't that concerning at the time. It was more of that, do we have enough population if the overwinter cyst survival is lower than a model's parameter that's built in at 50%. When you look at the dropping out of the outliers, you reduce that 19 to 20, it drops to 12 to 19, putting our predicted values anywhere from about just under 70 to about 130. With an average prediction of being about 100 cysts per liter. This is more closely to what we observed in the fall, in October, 76.2. So the key things to really connect the dots here. By the time we get our observed maximum in October, the harvest is starting. So now we're removing cysts from the system. So that's going to affect our counts during that time frame. The thing, if you remember from previous tag meetings talking about 2023, is we were just suppressed. The cyst counts were low going into the season. And so even though there were 4 or 5 generational spikes of females producing cysts, it really was on that density independent side where there just weren't enough females to actually get the population going. Luckily, we had those warm temps that persisted into the winter. that allowed them to get that extra generation. And I think that's why the bulk of our cyst production was observed in October. Then we have the quality issues from the year before, and that all kind of came together. So the really nice thing about what we saw and what's going on is, yet again, the model that is not designed to work in the parameters of the lake that we are experiencing is still getting us closer. We still fall within that 76 is above that 69%. So it's still useful in predicting the fall outcome in the spring, even in conditions that it wasn't really designed for. That's kind of the bad news portion of this. Moving into the 2024 forecast. Bad news side of this is we have this early hatch that Connor just mentioned, got knocked out in February, so don't get to use any of that data. And we're forced to use just those 4 runs in January. So instead of being a range, like last year it was 19 and 20, we get a single point. And because we have that, 34, 78, and 2 9s, we get a 32. That's what the model's predicting. 130 cysts per liter on this density dependent side of the curve, where perhaps we left a few too many just based on that particular data set. When you remove the outliers, anything that's 2 standard deviations above the mean, the second graph, it actually backs it back up, and we're centered right over the curve, right at the top of the peak, 27.96. For predicted value of about 180 cysts per liter. So as far as coming into 2024 with the reset of salinity, the high temperature, the fact that we didn't lose nuclei early in the spring with that short cold snap, we're actually in a great position for cyst production this year, going through the starvation cycle early. Really the thing that we're going to have in 2024 is there's more times for more generations. And it's really just going to depend on which side of that peak we're going to be on, which pathway we're going to take. We will know August once we've seen is it a lot of adults with few smaller root sacs, is it fewer adults with bigger root sacs. We'll get a hint of the pathway. Luckily, again, the model tends to tell us where we're going to go, and then we can retroactively look at how we got there. But this is kind of a nice position to be in, especially after the last few years. We're returning more to normal lake conditions from what we have seen from 1999. Any questions? Okay.
Awesome. So feel good, at least salinity wise, as well as brine numbers wise. It looks like they're back into doing the right thing, or at least getting close to it. All right, Gary.
Okay. All right. Well, first of all, I want to be optimistic with what we're hearing right now. I think that I don't want to be too optimistic, but it seems like we have turned the corner on things. I think this would agree too. Here's the results from last year and average in terms of phytoplankton, the counts in our lab. And the chlorophytes are about where they're normally at. The green line here is the first 3 months of this year. The blue is last year, and the red is a 5-year running average, or from 2018 to 2022. Not a big change in the chlorophytes. We see a lot more variation in the diatoms, the bacillariophytes, and a lot more variation in the cyanophytes, the blue-greens, in the data. And in particular, it looks like in July of this last year, we had a much larger increase in diatoms than we normally see. And we saw a much smaller amount of the cyanophytes going into the winter here. What we are seeing, however, that's the big difference in the phytoplankton composition in the lake, is others. We're getting a lot more variability in the phytoplankton than just the chlorophytes, the celeriophytes, and cyanophytes. And the increase that's up there in those others is, to a great extent, again, a reemergence of what we have seen in the past in the euglena in our samples. And that euglena increase is in specific locations on the lake. Most of it is at 2 of the sampling sites, actually 1 of the sampling sites, so it pulls all the others. So we're seeing that. In the previous presentation, the comment was made, or the examination was made of the chlorophyll A earlier, and it is really evident here that the first 3 months of this year are much closer to the 5-year running average from 2018.
Anyway, we got a technical difficulty.
Knowledge.
Because I gotta do this. Start sharing.
Okay. Okay, what you can see in 2024 so far, it's much more similar to the 5-year running average that we have, which is the red line here. Last year, 2023, as was just pointed out, is way off. A huge spike in early chlorophyll, and if you notice, it goes down to very low levels in the summer and well into the fall compared to the 5-year running average. This, I think, explains a lot of what's going on that we saw that was anomalous of 2023 in terms of the shrimp dynamics. And these are the same figures that you've just seen in the previous presentation. But what you can see is that the nuclei are already peaking well off from either the 5-year average or last year's average. Way early. Last year, we saw a peak in the juveniles that was we saw a peak of the juveniles later, which is what you would expect with the later appearance of the nuclei, but we had far fewer juveniles than average in the lake. However, when we go to adults, we actually had more adults, but it was not that much off from the 5-year running average. The big difference when we look at the adults here is that the ratio of females with eggs to the ratio to the number of females with cysts, we see that the shrimp the females were largely producing cysts rather than eggs. Why? Well, go back to that chlorophyll A value. Food was really low. That makes them shift to producing cysts. The high salinity makes them shift to producing cysts. And so you say, well, they're producing cysts. The cyst number should have been up. Well, the cyst number was well below the 5-year running average. Why? Because they had no food. They shifted to cyst production, but they didn't have the food to make the cysts. So last year was a strange year. This year is strange given that it started off so early compared to the 5-year running average. But the problem is now how it's all going to work out, but we are getting back, I think, to a more normal case.
There, you know, we do have over cyst counts, but there hatchability of the cyst. I know we don't do overwintering survival anymore, but it was way, way down.
Yeah.
It could have also affected your model.
Right.
Compared to the average.
Yeah, sometimes I wish we're continuing to measure that over winter survival.
I can tell you our numbers were around 50% hatchability, but that's at 24 hours.
Right.
Whereas, you know, this year we're closer to 80. Yeah, that's.
Your hatchabilities always were higher than our hatchability.
Yeah.
So that's what I think is going on here now. And that's a lead in to what John wanted me to do, which is to talk about the food web model in the Great Salt Lake. And I can happily say the complete model is put together now for the food web. We not only have, in the past, we had the pelagic, the shrimp, phytoplankton and shrimp and greens part of the model done. We now have the benthic portion of the model almost completed, almost. We're waiting on Mike to get done with the birds down here. So, what do we have? Let me just remind everybody what this model is. It is built completely on experimental data. It is not built upon any of the observations in the lake itself. It's built on experiments where we grew the different phytoplankton, the different salinities, temperatures, nutrient levels, grew the shrimp at different amounts of food, different temperatures, different salinities, and then Mike and Joe Caudell for the grebes did all the work on the energetics, the bioenergetics. We did the same things now for the benthic portion of the food web. We grew microbialites at different temperatures, salinities, nutrient levels. We grew flies at different microbialite levels, temperatures, and salinities, and we don't have the bird data yet. And this is a huge number of experiments. And some of these experiments, 5,929 experimental populations were used just to get at the shrimp numbers. Over 1,000 now for the microbialites, and for the flies are well over 2,000 experiments done. So this all can be put together, and the reason why there's an alarm here is because this green arrow is not known yet. So the computer program says, we can't do anything because we don't know what this connection is. So if we take that connection out from the model. The black line here is the addition of the bioenergetics of the grebes into the model. The black line here and here is now the linkage that we often talked about between the microbialites and the pelagic portion of the food web. We've added that in now. And when we do that, this is what all of the output looks like, and I'll talk about that as I go through this. But let's start with the effect of the grebes on the shrimp. The seasonal loss to the grebes of the shrimp population comes out to be somewhere about 12%. Now that 12%, because this is a complete food web model, when the grebes actually may eat at any one point a lot of shrimp, but when they eat those shrimp, that makes more food available for those shrimp that are not eating. And that leads to then better transitioning into the stages of shrimp that the grebes would eat, and leads to then continued reproduction. So that is the effect here of the grebes on the shrimp, about 12%. And remember, that's over what, about a 3-month period? Like,
3 to 4.
3 to 4. Yeah, it's built into the model, and the way the model is set up is once they reach a certain, they depress the shrimp numbers to a certain point, or the shrimp numbers get to a low point, they depart. That's built in a variable time period in the model. If, let's look at, oh, let's look at the benthic portion here, which is the new part to talk about. The red bars here are what were observed in the lake from 2017 to 2019 by field measures by Kate Bear in her PhD dissertation. The blue lines here, bars here, are what the model predicts. So this is the microbialite density of chlorophyll A per centimeter squared. Talk about a problem. Working with pelagic is easy, it's liters. Now I gotta switch to the benthic and everything is in terms of. And it gets even worse because then we gotta at some point convert centimeters squared into liters to get the interaction between the benthic and pelagic. So units have been my headache recently. So anyway, it does pretty good. It gives you an R value of about 0.69. It's not statistically significant, but there isn't a lot of sample here either to compare. We only have really 4 data points. And you can see it matches up fairly good, overestimates in June and underestimates in August, and December is close on. That could be fine-tuned in terms of the effects of temperature and salinity. It does absolutely great in terms of brine fly larvae. R value of 0.98, and you can see the red and blue bars match up very closely. And if we go to pupa, it's also very close. So the benthic portion of the model, now that we finished it, seems to be well along in terms of predicting what's going on. The tightening up here needs to be the microbialite section here. Now, the interesting thing is we built in the linkage between microbialites and the phytoplankton and flies on the phytoplankton, how this then affects the shrimp. When we do that, the lake level has a big effect because you got this microbialite there. And this microbialite, if it's covered by lots of water, the effect of the larvae and the microbialites on the shrimp becomes diluted. Because you got to convert each centimeter squared into some volume per liter. Volume. So the net effect is that if there's no linkage at all, there should be no change in the shrimp numbers. And we're using a simple index here of shrimp numbers, which is adult equivalents per liter. So as the water gets deeper, there's less effect. So let's say on average, the water is about 2 meters deep above the microbialite. Predicts that above the microbialites, the shrimp should be approximately 50% greater in the water column than out away from the microbialites. There's more shrimp over the microbialites. And that's because these larvae, to a great extent, what they're doing, you can measure this, what they're doing is they're scraping away at this microbialite and they're literally spitting out the cyanobacteria, the cyanophytes. They don't like it. They want the diatoms. And so they're not ingesting as much diatoms as we've measured this in experiments. And they're putting that up in the water column. As much as 11 milligrams, no, I'm sorry, about 11 micrograms of chlorophyll A per centimeter squared gets released. Well, the microbialite's at 400, let's say, or 200, somewhere in there. So about 11 micrograms they're spitting out. Now they're eating some of it, but they're not eating all of it. And that gets then diluted in the water column. And those shrimp that are there are churning this up. Why then, if it's the same amount being released in the water column, why as the water gets shallower, does it have a bigger effect on the shrimp? Because it's now concentrated more. It's not diluted in as much water. And that means each shrimp then survives better, reproduces better, transitions between life stages better. So that if the water goes down to half a meter above the microbial life, the shrimp concentration gets up to about 350% of what it is in the open water. Shallow water is good. Well, problem is, if this goes to too small a value here, the microbial life dies. Right. So this is not a continuing function, but you can see there's a rapid increase. The model builds this in terms of how dilute this release of food is. But that's a big difference, 350%. Let's say observed from Kate Barrett's dissertation is about a 60 or 70% increase. So it's somewhere between 2 and 1.5 meters depth. Well, when you take into account using Rob Baskin's measurements of how much microbial life is out there, and then you dilute, it's not just the surface area of microbialites. There's a lot more water out there than just over microbialites. When you dilute all that, the percent change goes down to about 2%, a little less than 2%, up to about 8%. So this is diluted drastically. So we've been talking about the benefit of the microbialites to the shrimp. And there is a benefit to the microbialites, to the shrimp from the microbialites, but it might not be as big as we think based upon just surface area calculations. And over the 5-year period, what we're looking at here is the data over 5-year average. The phytoplankton is increased by about 2.5% by the release primarily of the cyanophytes into the water column. Shrimp are increased overall by about 2%, and the cyst production does even better. It goes to 4%. Yeah.
Are they continuing to do this study in the really dry years? Have they continued to do that kind of thing?
We don't have measures. That's the problem. You don't have physical measures other than that period when my PhD student was measuring this. And that was, what did I say, years?
It was 19 or
17 to 19, 2017 to 19. So basically that was 3 years. We don't know. We don't have those measures. That's one of the weaknesses we have is on the actual lake measures of what's going on with the flies and the microbialites. We have the laboratory measures to make the kind of projections, but we don't have the actual field data to compare those projections to, except for 2017. Sorry. So anyhow, there is this effect connecting the pelagic being affected by the benthic in the lake. And there's also the effect in there of the actual brine shrimp scraping some of the microbialite, but that seems to be far less important than this release by the flies of the phytoplankton, or creating phytoplankton by putting the cyanophytes into the water column.
Yeah, Gary, it's not just food they're relying upon over these microbialites, they're relying on oxygen as well.
It could be, yes.
Yeah. And then when they graze out the benthic area, the pelagic area, that's really the only place that's not in oxygen.
At that time, the high in oxygen content, yeah, was true.
Yeah.
Yeah. Okay, so let's look at the model output from the pelagic community. This has been presented numerous times by putting the link between the pelagic and the benthic into the model. It increases the predictability, the R value, by about 0.01. So it didn't add a lot to what we previously looked at. You can see that the phytoplankton chlorophyll A values are matched pretty well by the model prediction. The nuclei numbers are matched pretty well. The juvenile numbers are matched pretty well, and the adult numbers are matched pretty well. and the addition of the linkage between the between the pelagic and the benthic communities increased cyst production October by up to 140 versus 127. So that's where the big change occurs, is it benefits the cyst production. Now that the model is put together, the model can now be expanded, not to just look at numbers of things and amounts of things in the food web, but the nitrogen cycle. That's where we're at now. And I am hoping to be able to have the results put together for the Friends of the Great Salt Lake meeting next month. But this is what that portion is takes. Here's an example of an experiment we just finished in the lab that was interesting. It was decomposition of brine fly larval bodies. And the interesting thing here is 1 week after you put the body into lake water, you can see in almost every case, the body got heavier. It's supposed to get less. It's supposed to be decomposing. It actually increases in weight. Why? Because the brine fly larvae keep their body salinities much lower than the water salinity. So in those first few weeks after they're dead there, those carcasses are essentially becoming made into beef jerky. They're taking in salt and being preserved. And then after a period of time, it starts going down, which is what we expect. And in fact, they're unlike the shrimp bodies, which decompose right off. Shrimp bodies are basically at water salinity levels. Whereas the larvae, fly larvae, maintain their bodies at much lower salinity. Here's what goes into the nitrogen cycling model. We have completed all the inputs from the pelagic side, which you'd expect. We have nitrogen content measurements on the phytoplankton, brine shrimp pellets, that's their poop, bodies decomposing, and of the cysts, we have nitrogen content, and then we get down to nitrogen content of feathers, thanks to Mike sending us feathers. We have of grebes, and then we have the amount that's being produced of each of these quantities. And, whoops, hitting the wrong button here. We have the amount being produced. Anything in blue here, mortality, reproduction, ingestion minus metabolism, that number comes straight from the food web model. Then we have to be concerned with the fall rate. Do these things float? They stay in the water? They sink fast? Because if they sink fast, faster than decomposition takes place, they could end up in the deep brine layer and separate it out. And then you have to calculate the rate of decomposition going on. And we're measuring, we don't have green feces, their decomposition. We have measures found in the literature for ducks that we're using, and we're measuring feather decomposition. Where we're missing stuff is here again on the benthic. So on the benthic side of things, we pretty much have all the nitrogen content measures being done. Matter of fact, this is probably being done this week. We have the amounts being produced. Either it comes from the model, the food web model, or we measured it. How about that? 739 pellets of poop per week per brine fly larva. This over here for the shrimp is something like 400 or 500 per week. These we don't have to worry about the fall rates more. Why? Because they're on the bottom already. They can't get into, well, I shouldn't say can't. Certain wave action can move through and move some of the substance. But since it's sitting on the microbial life, it is not going to easily fall off into the deep brine layer. and be concentrated there. And then we need the decomposition rates. And this is starting this week. This is starting this week. This is completed. This hasn't started yet, and this hasn't started yet. So those are the numbers that we need to get to finish building out the model for nitrogen. And just to give you an idea, here's what the nitrogen cycling model looks like added to the food web model, just for the pelagic portion of things. Here's taking into account death and decomposition of phytoplankton, production, and that's the green here. And then we have production and death of brine shrimp and decomposition here. We're going into the upper brine layer, lower brine layer. Then we've got production of fecal pellets separating between the two layers. And then we have the bird effects down here in terms of fecal production and in terms of feather production or feather loss production. This is what gets stored in different pools within the lake, and this is how it comes together between the flows, which are here, and the sequestration here. And so there'll be a matching model over here for the benefit portion, and that's where I'm at right now. That's what I have to tell you guys about questions.
I'm still perplexed on how the weight of your brine fly larvae is actually going up.
Because I'm trying to remember, I think the vines are about 6% salt salinity. And if you got them in water that's 8 to 160%, their bodies now are taking in the salt over time. It's the same, it's the same thing that happened with the Native Americans on the Great Salt Lake.
It's dry weight.
Right. No, but they're live weight when you put them in the water.
With a live weight, you would be extracting water from the bodies through osmosis.
But you're also going to get salt coming in. It's exactly what I was going to say. Native Americans did with the Mormon crickets. They got jumped into the lake, and they had, potato chips. They could harvest them and dry them, and they had salty potato chips because the Mormon crickets took on the salt, and they dried out and they're preserved. That's what's going on
Somehow
here.
the salt gets into the cells.
Yeah. Yeah. And the other interesting thing that we're finding about the larvae, they're pellets, they're poop. Technical term is frass. Their frass is extremely dry, even though they're living in an aquatic environment. It's about, I want to say it off the top of my head, we just came up with this measure last week. It's somewhere like 15% water content of it. That is really concentrated then. But if you think about it, why would you want to, if you're a larva, why would you want to dump water out? Fresh water, which is essentially in your body, and have to try to replace it from the lake around you.
But then with your decomposition rates, won't you at some point stabilize at a certain value? It will never become zero because the salt will still be in there.
Correct. You're right. And
So
that's
you
why
might
the
be-
current goes like that, and we have to take that into account, that once it's stabilized, that's 100%. Yeah, has to be built in that way. It's just too much. Other questions?
Wouldn't brines like normally sink anyway, because that's where they want to be in the bottom?
Yeah, that's why they're on top of the microbial. So why worry about their sinking rate of the body? Because they're on the bottom already. Except it's not a deep brine layer or bottom.
So they would be more dense. To make it to the bottom. That's right.
Right. But they're also grasping on. Other questions?
We do have a comment from
Okay.
Bonnie Baxter. It's
Yes,
saying,
Bob.
"Hi Gary, our studies show the mats are probably less than 1% cyanobacteria. Also, many species of other bacteria, archaea, eukaryotic algae, and fungi. So the mats may supply a very diverse food supply. Question about your feeding experiments, cyanos versus diatoms. Do you know that chlorophyll is refusal of food? Or could it be chlorophyll is released when you munch on a cyano, but the diatom structure prevents immediate release?"
It could be, there is some by crunching on a cell that releases chlorophyll. That does happen, but we also know that it is complete, cells being released into the water column in the feeding by the larvae. And that's because we can look at what's actually there in the water we can sample. I mean, that's the advantage of doing this as a laboratory experiment, because if you try to do it actually in the lake itself, it's diluted so fast you wouldn't be able to see it. But if you can do it in a 15 milliliter test tube, you control all that dilution and everything else. Does that answer? Okay.
Yeah,
Awesome.
Gary, can you hear me?
Yeah, here you go.
I'm just wondering if what you're measuring is just chlorophyll.
Well, when we did the experiment in the lab, we measured both chlorophyll through the fluorometer, and we looked at the water and looked at what was in the water, and we saw actual cells of the algae.
Okay, so you did microscopy and chlorophyll.
Both, yes.
Okay. Okay, thanks so much.
Okay. So anyway, there's the story when you put benthic and pelagics together. It gives us some idea. I can't say that those figures of how much transition between the two takes place are exact, but they're at least ballpark estimates, and they're not as great as we maybe thought they could be, but they're not necessarily trivial either, especially for cyst production.
All right, thanks, Gary. We're going to go to the last presentation by Mike, and Lauren's not here. I saw she was online, but the bioenergetics, we're taking a break from today, and going to talk about something a little bit different. Although I will say that Lauren's work on the bioenergetics study is proceeding, and again, thanks to our contributors, which is the Utah Wetlands Foundation, the Delta Waterfowl, and especially SFW and Water Resources, and we're actually looking at expanding our bioenergetic study to include another student, thanks to Water Resources, which is starting to, or is, we're working on a contract with them to be able to concurrently run another student to help Lauren, since she's mostly concentrating on the waterfowl portion of it, but to kind of do the shorebird portion of that study. So hopefully that gets done ASAP and we can get the new student added to that. So that's in process. That's just a quick update. All right, go ahead.
Thank you. You know, when I was leaving home as a child, my childhood, my mom turned to me and said, "Matt, if you're gonna survive in that world, there's one thing you need to know, and that is never stand between a biologist and lunch." So I am going to keep my comments short and brief because I don't want to get trampled. At the last TAG meeting, Lauren had my graduate student talked about our bioenergetic model. I'm not going to do that. But there's another project that's not funded by TAG. It's actually funded by the Utah Agricultural Experiment Station. And it's looking at duck nesting in the market for Great Salt Lake. As far as the Great Salt Lake is concerned, there's really two important periods for all of the ducks that are staging here. We're all familiar with that, but there's also ducks that nest here. And it turns out that they're of a continental concern. And that's what I want to cover here. With duck nesting, it is a tale of two worlds. Before 1980, life was wonderful for nesting ducks. There weren't very many predators here. There were thousands of ducks. We were producing tens of thousands of ducks every year from the Great Salt Lake marshes. In the early 1980s, it flooded. All of the areas that ducks used to nest were underwater. That's water coming from the Great Salt Lake as hypersaline, so it killed all of the aquatic vegetation. During those years, the ducks all got up and they moved further north into the flyway, nesting in Oregon, Washington, Canada, Idaho, Montana. After the flood receded, the marshes came back, the vegetation came back. A few ducks came back, but not very many. And so since the floods, things have gotten very bad for the ducks. And that's in part because they came back to a community where now there were red foxes, there were raccoons, now there didn't used to be. And skunk numbers were much lower prior to 1980.
And cats.
And so what I'm going to do is look at what's happening here, the nesting duck, and the duck support. There are three species of ducks that nest here. Gadwall, there's millions of those in the continental population. Mallards, there's millions of those. And for those two species, they nest primarily in the Prairie Poplar region. The numbers in the Great Salt Lake marshes are small compared to the continental population. The populations are important for people in the Intermountain West, but continental-wide, we don't have much impact on mallard or gadwall populations. It's different for cinnamon teal. Cinnamon teal is a much less common duck. There's only, during the heyday, there were 300,000. We don't have hardly any data on the actual number of cinnamon teal in the population, because in the fall, they've already left primarily before the hunting starts. Most populations we monitor from bad checks. And also in the fall, they are lumped with green-winged teal. And green-winged teal are much more common, so we have really no idea how many cinnamon teal are in the population. So that's a difficulty for us. But if you look, the Great Salt Lake isn't a part of the breeding population for cinnamon teal. Prior to 1980, over half of the cinnamon teal in the world nested on the marshes of the Great Salt Lake. Half of them. That's no longer true. What I want to cover is what's happening and why it's happening. One thing that we know is climate is changing. There are two things that are happening or predicted to happen in the Intermountain West. It's going to be drier, less precipitation, more evaporation, and climate extremes are supposed to occur at a higher frequency. And that is something we've had in the last 5 years. What we have here is data on precipitation, snow, for the last 5 years. To make it obvious which is which, we have had 2 drought years, 2021, 2022, that reduced Great Salt Lake levels to historic peak. We also had 2 historic rain events. In 2019, we had precipitation, especially in the spring. It rained all spring long. Vegetation was very flush. So that was the highest spring rainfall we've ever had. And of course, last year, not much spring rain, but that was the heaviest snow levels we've ever had. So we've had, in just a 5-year period, 4 setting records, and they went both ways. So I said, let's give it half of, let's see what this is doing to the ducks. And so we looked at them. Here, we're going to start off looking at nest initiation. I go out into the marshes. I find hundreds of duck nests, and I've determined that rate. Nest initiation rate doesn't change based on climate. It's always the same, very little variation. Holy cow, just 1 or 2 days from one year to the next. Clutch size, though, is highly significant. And if you look at it, the clutch size is highest during the years when we had a lot of precipitation or a lot of snow level. Okay, so how about duck nest numbers? Here are the results. Really large variation. I'm running transects here, so the numbers on the total number of ducks out there is the number on transects. But look at the variation. Cinnamon teal, we had 20 nests, 59 nests for the 2 drought years, 2 wet years, 267. Not many here, but a lot of variation among years, and they were highest during the wet years, especially at spring precipitation. And that agrees with what people find as very possible. That basically what happened is ducks move north in the flyway. If they find someplace that they like to nest, they stop. If they don't like the Great Salt Lake, which is where they get first, they keep flying. In 2019, they liked what they saw, so a lot of them stopped. And the same pattern occurs for every duck species. There's no variation across years while having the same effect. Well, how about looking at the fate of the nest? We monitor them and put cameras up so we know what's happening to them. Abandonment rate, this is the number of nests where the female just abandons. They're probably, for the most part, females nesting for the first year of their life. And there's no significant difference among years in abandonment rate. Look at depredation rates, though. 2 wet years, nesting success. Well, let's look at depredation. 2 wet years, depredation rates were low. Drought years, 84, 96% of all nests were depredated. And so if you're not being depredated, you're not being abandoned, we have success. Continental wise, we say a 15% reproductive rate is what's necessary to sustain a population. So we did well during the 2 wet years, not so much during the 2 dry years. I should point out the black line, that is a normal year. We have 1 normal precipitation year, 2 wet years, 2 dry years. So successive nests is impacted by climate, what's happening. We also looked at predator populations out there. We did that by putting nest cameras on bridges so that the birds, for the most part, are nesting on the dikes, on the dams. We put nest cameras where there are culverts and a bridge, so the predators, as they're moving along, the dams are going to have to cross this, and we count what we see. And we find mainly skunks and raccoons. Occasionally we'll find a coyote, occasionally a red fox, and all sorts of things. This one was taken this last year. That is an emaciated raccoon. I'm pointing that out to you now because you'll see the results. Remember, that's the heavy snow year. That year, where snow is monitored in the refuges itself. So this is how much snow is on the ground in the marshes. And here are the results. Well, they have, unfortunately, we monitored predators for 3 years, not all of them. But if you look, here is a heavy snow year compared to a normal year or a drought year. Skunk populations collapsed. raccoon populations collapsed, total number of predators collapsed. And so that's one reason why the ducks did so well last year. There simply were not the predators out there that there had been historically during the drought years. So here's what we found. Duck numbers and densities were both positively correlated with spring precipitation. Skunk counts were negatively correlated with local snowfall. We had a lot of snowfall, they all died. Same thing is true for predators total. Nest depredation rates negatively correlated with snowfall. There's no predators because the snow killed them all. Depredation rates go down. This should be nest success rates. I have the wrong word there. They were positively correlated with, no, I take it back, that is correct. Nest depredation was positively correlated with raccoon abundance. Flight size was not correlated with anything we looked at. Before we started the bioenergetic model, we were monitoring food levels. So we didn't measure food, and you would suspect that, well, maybe clip size varies with how much food the ducks have, but that wasn't what we were measuring. We were measuring climate. And you see the predator in that one? These are nest cameras. We put nest cameras up. You see it? We'll do this quickly. This is him right here. You know what it is?
Skunk.
That is a skunk. How about that thing? Holy cow. Looks like my grandma's wig. That's a raccoon, very close to the camera. How about that? See him? Cute little face looking at the camera. That's a skunk. How about that one? That thing's terrified us when we first brought that thing out. It's like, holy cow, what the heck is that? You know what that is? It's a sandhill crane. And it's eating ducklings, not the eggs. So the eggs in this nest just hatched, and he's coming down to help himself with some ducklings. How about this one? Recognize it? See it? It's over here. It is a long-tailed weasel. And so here's what we found. Here's all of our nest camera results. If you look at the predators that are taking nests, there's a lot of them, but there's only two that really count. Vast majority are taken by raccoons and skunks. 61 out of 75. You don't need to worry about these guys. You want to help ducks. You don't want raccoons and skunks out there. The bottom line is, in these marshes, you can have a million predators, skunks, and raccoons if you want, but you can't have nesting ducks. Or if you want nesting ducks, you really can't have raccoons and skunks out there. And that's in my presentation. I presented that, by the way, because it is our mandate to manage the Great Salt Lake and the marshes around it in such a way that they do not have an adverse impact on avian populations. And we've done a great job of that for most birds, but for cinnamon teal, they're in a world of hurt. And if they're in a world of hurt here, then the continental population is in a world of hurt. But it basically means I can't tell you how the total population of cinnamon teal has decreased since the 1980s. Nobody knows. But what has happened is the Great Salt Lake marshes used to raise half the cinnamon teal in the world. Now they raise almost nothing. So it's not a happy day for cinnamon teal. Thank you.
One weird thing that I noticed last year for the first time that I've ever noticed this was cinnamon teal here in the December, January time frame. Usually they're way south of here, but we had a ton of them here. There was a lot of cinnamon teal harvest going on here in the middle of the winter, which was different. So I don't know if that has something to do with climate. I don't know if that's a shift now with climate change, that something's moving them farther north or what, but that was an oddity from last year.
I observed that too. We did some bag checks and some of the WMAs, and we were finding cinnamon teal. And that's the first time that's ever happened. Cinnamon teal are usually the first species out of here.
Yeah.
And that's the problem, that they're out in August. They migrate very fast. And most of them still do. There's a few that remain here long into the fall, but the vast majority skedaddle. They move to Central America, South America. So our hunters don't like them so much because they're not here with people in North America who go that time.
All right, thanks, Mike. Well, I'm gonna conclude this meeting real quick, so we can all, yes,
Would you let me eat this, I'll just let me take a photograph?
sure.
You got it.